In this video, we're going to talk about curve sketching of polynomial and trig functions. Just a quick reminder about some of the things that you look for when you're analyzing a function in order to sketch the graph. So remember, we always want to look for domain and range if we can, intercepts, asymptotes, and any symmetry it might have. And then it's really important to find where the function, its first derivative and second derivative are equal to 0. All right, let's analyze this function. I have a quartic function, so x to the fourth minus 12x cubed plus 48x squared minus 64x. First thing I'm going to try and do is factor this thing. So I'm able to pull an x out because all of these terms have an x in common, and then I'm left with this 4-term polynomial that's a cubic, and I can't factor it by grouping. I can't split it and get the same factor on both sides. So I've got two options. I can graph this function and find any of its real zeros, or I could do the p over q, where I list the factors of this guy divided by the factors of 1 or that coefficient there. And I'm going to prefer to graph it and find that 4 crosses through. So that means that 4 is at least a real 0 here. So I divide by x minus 4 because that would be the factor, and I get this quadratic that actually factors quite nicely to x minus 4 times x minus 4. So all of those combined make this factored into x minus 4 all cubed. So this is my function all factored out. It has no symmetry. I plugged in negative x, didn't return the same or the negation of that function, so no symmetry. I was able to find the x and y intercepts, so 0, 0 and 4, 0. So the information that I have is that this thing is a quartic, and I've got two intercepts at one's at 0, 0 and one is at 4, 0, and they both have odd multiplicities, so I know they're going to cross. So I'm imagining that it's going to make some kind of W, because that's what a quartic does. It's positive, so I know that the domain is going to be all real numbers. And let's get to these 2 points in just a moment. So just given this information here in blue, I don't have a lot to go on. So I take the first derivative, and I'm able to pull out a 4, and I've got a cubic left, and unfortunately it's not factorable by grouping, but just like what I did with the cubic on the previous slide, I could do the p over q, so the factors of 16 over the factors of 1, plug those in, or I could graph it, which is what I did, and I found that it has two different real zeros, one at positive 1 and one at positive 4, and this one bounced, so that was a power of 2, and this one crossed, so that's a power of 1. So 1 and 4 are my critical numbers. So 1 must be one of these dips over here, and that 4 obviously is my intercept. So then I take my second derivative, and luckily this is a quadratic. I could pull out a 12, I can factor this, I don't have to do any extra stuff there. So I have two critical numbers here. I've got 4, which I already know from that intercept, and positive 2. So when I plug in 1 and 2 into my original function here, I get an output of negative 27 for f of 1 and negative 16 for f of 2. Now I'm not quite sure if that's exactly the shape at this point, but I can tell that those are probably my points of inflection, or relative or local max or min actually. So that helps me figure out that the lowest point, or where the range starts, is going to be negative 27. So this leads me to testing different intervals around my critical numbers of x equals 1, 2, and 4. So if I pick a number between negative infinity and 1, that gives me a negative first derivative but a positive second. So that means the function is decreasing and concave up. And then when I plug in 1 into the original, it gives me that output of negative 27, which is my lowest point. The first derivative is 0, so that means it's a horizontal tangent. And the second derivative is positive, so that means it's a relative min. So that's my lowest point, which I kind of already figured out in the last slide. And then I plug in a number from 1 and 2, and I find my first and second derivatives are positive, so that means that my function is increasing and concave up. And then I plug in 2, which is another important point here. I get negative 16, which I found on the last slide. And my first derivative is positive, but my second derivative is 0, so that means it's a point of inflection. So the function goes from increasing to increasing, but it goes from concave up to concave down, which is what causes a point of inflection. And then when I test a number between 2 and 4, I find a positive first derivative, negative second derivative. So that means the function's increasing, concave down. And x equals 4, well, we know that is a x-intercept, and that's also a point of inflection because I've got zeros across the board. And then from 4 to infinity, so 4 beyond, I've got positive derivatives here, so that's increasing and concave up. So when I look at the graph of this thing, it's a little different than what I guessed it to be, but it's coming down, it's decreasing, and it's concave up until about x equals 1, so that is going to be my relative min, and then it turns to be increasing here, but still concave up. And then here's a point of inflection at x equals 2, so it's still increasing, but it's going from concave up to concave down, which creates that shape right here. So it's concave down, and that's another point of inflection and an intercept, and so it goes from concave down again to concave up, all increasing all throughout here. And now let's take a look at how we analyze and sketch a graph of a trig function. So I have a fractional function here that is cosine of x all over 1 plus sine of x. So let's see what I can analyze here. So what I'm going to do first is try to find my intercepts. So my x-intercepts, I make y 0, I solve for that. I cross multiply cosine of x over 1 plus sine of x equal to 0 over 1. So when I cross multiply, this 1 plus sine x goes away, so it's really cosine of x is equal to 0. And between 0 and 2 pi, so around the unit circle, cosine is 0 at x equals pi over 2, or 90 degrees. And then the y-intercept, I plug in 0 for x, and cosine of 0 is 1, and sine of 0 is 0, so that makes it 1 over 1, which is 1. So our y-intercept is at 0, 1. So that means I have my intercepts for one cycle, and obviously this is a trig function, so this is going to repeat. So this information is useful. And the next thing I'm going to do is find my vertical asymptote. Because this is a fraction and I have 1 plus sine x in the denominator, I need to set that equal to 0 to figure out what x can't be, or to find my vertical asymptotes. So that gives me sine of x is equal to negative 1. And from 0 to 2 pi, so on the unit circle, that's at 3 pi over 2, or at 270 degrees. And that's going to repeat every 2 pi n, where n is an integer. So what I know about my graph is so far this. So I found my first asymptote in the positive land at 3 pi over 2, right, because that's what made 1 plus sine of x 0. And so I subtract 2 pi and I get negative pi over 2. So my two asymptotes that allow me to find my first curve are between negative pi over 2 and 3 pi over 2, which will be the interval that I'm going to test for concavity and such. And then I also happen to know my very important intercept, so 0, 1 and pi over 2, 0. And I'm estimating that it's probably going to look like this, but let's take the derivatives and test intervals and see what we really get. So when I take my first derivative, I'm going to use the quotient rule, and I actually wrote it out here. And so when I combine all the things in the numerator, I get this quantity, negative sine x minus sine squared x minus cos squared x, and then I bring down the negative sine x, and I take out a negative from sine squared and cos squared of x, and I get sine squared x plus cosine squared of x, and if you didn't know, that is actually equal to 1. You can look up the proof, it's beautiful. So that means I have a negative sine of x minus 1, and if I pull out a negative there, that's the same quantity in the top and bottom. So one of these goes away, so I'm left with negative 1 all over 1 plus sine of x. And when I set that equal to 0 over 1, I cross multiply, and unfortunately it gets rid of the x. So I don't have any critical numbers here, but let's try the second derivative. So to find the second derivative, I take my first derivative and I work through that guy, take the quotient rule. Nothing fancy happens here. So I end up with cosine of x all over 1 plus sine of x all squared. And then this zeroes out, so it's really just cosine of x equal to 0. And on the unit circle, cosine is 0 at pi over 2 and 3 pi over 2. But I have to get rid of 3 pi over 2 because I happen to know that that's an asymptote. So really, I'm just looking at pi over 2 as a critical number. So I take my interval, which is negative pi over 2 to 3 pi over 2, and I happen to use that because I know that that is an interval on which my function exists, and negative pi over 2 and 3 pi over 2, remember, are my two vertical asymptotes that I know for sure. And the critical numbers that exist between there are my two vertical asymptotes, so negative pi over 2 and 3 pi over 2, and that lovely pi over 2 in the second derivative when it was set equal to 0. So here are my intervals, which test every number, including these and the intervals on the outside. And so we can confirm that negative pi over 2 and 3 pi over 2 give me vertical asymptotes because they produce undefined answers for all the things. And then I test a number between negative pi over 2 and positive pi over 2, and I get a negative first derivative and a positive second derivative, which means that my function is decreasing, but it's concave up. And then my other interval to test is pi over 2 to 3 pi over 2, which are both negative when I take the derivative and I plug in a number. So that means the function is decreasing and concave down, which leaves pi over 2. So that gives me a 0 on the function because I know that that's a critical point, and also a intercept. And so it's got a negative 1/2 first derivative and a 0 second. So that means that it's a point of inflection. So that means that although it's decreasing right around that point, it goes from concave up to concave down. So that's why it's a point of inflection. And here's what this graph is going to look like. So here are two asymptotes, here are two intercepts, and this is actually point of inflection as well. So it matches. We've got a vertical asymptote here, we've got a decreasing function that is concave up, and then a point of inflection right here at pi over 2, and then now it's decreasing and it's concave down. All right, that's going to do it for this video. Thanks for watching.